about, and I don't have the title here in my notes, but it's where it says finding the definite integral using substitution. And it says there's two methods there. You can find the indefinite integral using the fundamental theorem of calculus and do it normally with x. And then we'll also look at how we could just substitute with u, which is my favorite way to do it. So I'll show you, can I show you my favorite first, even though it's method 2?
Yes.
Okay. So what I would do is I'd see this and I'd be like, ooh, I've got an inside function, and that means I should let u equal something. This is normal. In fact, if you were doing the indefinite integral, you would get this substitution, and then it becomes easy negative u to the 5 over 5 plus c. That would be what you would do if it was an indefinite integral. Now, my favorite technique is to use method 2. If we're substituting u, that changes the bounds. Because if u is equal to 5 minus x squared, well, then when the lower bound x was 1, that would make my u equal to 4 when I plug in a 1 for x. And my upper bound, when x was 2, that would change my u to 1. Now, personally, I need this for method 2, but I actually wouldn't even do this. I would probably start with keeping my number here 1 and 2, because that's what I started with. Then I would do my substitution and change my bounds. Now, it's important that you label lower and upper, because the tendency is that normally when we do definite integrals, we have a smaller number on the bottom and a bigger number on the top. That's sort of what we're used to, right? But here, my lower bound changed to a 4 and my upper bound changed to a 1. So if I was doing this, my favorite technique, I wouldn't do indefinite integrals. I would have this, and then when I change it to u, I would change my bounds right in there right away. A common mistake for students is that they do the u substitution, but they keep 1 and 2 there. Technically, that's an error. It's not true. When you change this to u, the bounds change as well. And so then you would get, right, integral, this is negative u to the 5 over 5. The top one is 1, the bottom one is 4, so we plug in 1, we plug in 4, we subtract them, and you would get 204.6. I'm going to erase my red parts here for method 1. So method 1 says, well, if you did the indefinite integral, then you could substitute back for x. That would be the indefinite integral for x. Then, if I did my integral with respect to x like this, it's going to be square brackets with this x from 1 to 2 with our regular bounds. The substitution, again, I'm going to promote method 2 again here. Whenever you substitute, what do you do to your integral? You make things look neater, right? Compared to the x's, which is more complicated. And if things look neater, they're easy to substitute into and easy to do the mental math or calculations. So that's why I really like method 2 better. But it's not hard. You could plug in the 2, you plug in the 1, you'll find out you get the exact same result as an answer. So the benefit of method 1, it's more like what we did with our indefinite integral when we use substitution, because we always had to go back to x for our answer. The benefit of method 2 is you don't have to go back to x. If you've changed your bounds, then your mathematics becomes a little bit easy. And on that first take-home quiz, or sorry, not first one, on the one you just handed in, there was like one question in there where a little bit of substitution really would have helped. And you might have seen that if you came for extra help and stuff like that, or talked to other people. You'd be like, yeah, there was one that you had an f of 2x. And if you just substituted a u in for that 2x, then life got a little bit easier. So, I will do my favorite way first. I would see that inside function of 3x. And even though, well, okay, I'm gonna do my really favorite solution on my own. Okay? Yeah, no, I'll just keep with this because don't want to get too creative here. It's all good. Okay? If I make that as a substitution, then du would be 3dx. I can get the dx by itself with the 1/3. I can substitute in. And personally, I would have done the bounds right away. So my original bounds here in red were from 0 to pi over 2. And my lower bound is still going to be 0. And now my upper bound is 3 pi over 2. I would go directly from there to there. Right? Because that's easy to integrate. Negative 1/3 cos u. It's going to go from 0 to 3 pi over 2. Plug things in, and you get 1/3. So for me personally, if you do a substitution, change the bounds right away. I find it somewhat, if I'm a student, if I was you guys at your age doing this question, I would find it somewhat difficult in my first step not to write the 0 and pi over 2 that were originally there. I'd have a very difficult time not writing the bounds because they're in part of the question. I'd actually feel like, are they going to take off marks because I didn't write something? You see? Can you see yourself feeling that? But then if you wrote it here, you'd be very tempted to write 0 and pi over 2 in the next one. And then you'd be like, well, I actually wrote something wrong. Writing something wrong usually means a mark deduction, because technically it's not true. If I change it to u but keep the bounds the same, I've made a mistake. So that's why personally I like to write the bounds again, because that's how you would naturally follow a question. You write what you see and then make sure you know that you should change those bounds. You can still use method 1 and switch back. So I would probably, this next part is where I do the plus c. I would probably go to this on this side directly from there without writing this plus c part. I wouldn't do the indefinite integral at all. And you get 1/3 that way. Was substitution really necessary in this question? This is a simple chain rule, right? This is one of the ones we did early. It's like, if the simple chain rule would multiply by 3, doing the integral would divide by 3. So for me personally, I'd probably just do the black and no substitution whatsoever. Because this is one I could do. I'm like, I can do this integral without doing any work. I would probably just do the black in this question because substitution isn't really necessary because the chain rule is multiply by 3 and that's a constant. So I could just divide by 3 to compensate. This is the This is the line where math is fun and frustrating at the same time. Okay, from my perspective, I'm like, this is fun. You've got different options to do it. You get to do more math in more different ways, right? And this is frustrating as a student. You're like, oh, I wish there wasn't like, why couldn't it just be the same way every single time so I don't have to think? Right? We have that, right? The thinking part is fun when you get. And I always tell students, they're sort of like, there's fun math, that's all the math you get, right? When you're showing a friend, or if you have a sibling in grade 10 and you're like, oh, you do it this way. If you have ever helped someone in something you know how to do, if there was a camera on you, you'd see that you were smiling because like, I know how to do this. I feel important and I feel good. I like this because I know how to do it. And then anytime you've got a take-home quiz from us and you're on that question where you can't get it, right? There's not a smile on your face like, oh, I'm so happy that the next half hour I'm going to struggle and probably not get the answer. And you're just happy. No, right? So there's math we know how to do, which is fun. And then there's the math that we don't. It's frustrating. And this can sometimes be frustrating because there's so many options. All right, do I see an inside function? Yes, that 4 minus x squared. Is it one where I should use substitution? Absolutely. So here I would do this as my first step. Figure out what my u's are, and this right away with my bounds. Because when I write step 1, I would probably find it very hard if I rewrote the question not to write the 0 and 2 there. But when I change it to u, that means my lower bound changes to a 4. My upper bound changes to a 0. And that's u to the half. So add 1 to your exponent and divide by 3/2. I've already done the simplification. If I was doing this on my own, I would definitely show the divide by 3/2 and then do the mental math in one extra step. And now it's not hard to plug in the 0. Always plug in the top number first. Plug in the bottom number. And you get 8/3. Can I be so bold as to not to show you the other boxes? Are you okay? Like, and now I'm really trying to influence you that I think this is the best method to do it. And keep your life simple that way. So if you're going to use substitution, I would say go with the bounds right away and switch. And now I'm going to show you a visual with a very simple example of why this works the way it does. So sometimes when you're dealing with complicated math and you're doing stuff, you're like, I don't really know what's going on, right? Like this one, we're finding the area from 0 to 2 under something I cannot visualize. Right? I have not had enough experience graphing x times the square root of 4 minus x squared to really be like, I know what this graph looks like in my head. So when we can't visualize things, things get a little bit tricky that way. But something that we could visualize, let's say I want to find the area between 0 and 4, and this is very similar to what was on our last take-home quiz. And I have some function with a 2x inside. which is a very simple chain rule. But if I visualize 0 to 4, I'm going to make this a perfect triangle from 0 to 4. With that triangle, you know that, let's even make the height 3. You know that this area, base times height divided by 2, is 6. Now, f of 2x, well, f of 2x has a horizontal compression by a half. Things are moving. If this is f of 2x here, what would f of x look like originally? F of x would have been much wider. It would keep the same height. Can you see that the areas would be different? Okay? And although this is a simple one, we can say, let u equal to 2x. Okay? What does that do? That means that my lower bound would be 0. My upper bound when x is 4 is 8, which makes sense because we had our original function. But du will equal 2 dx. In other words, dx is half du. So now if I look at the integral from 0 to 8 of fu, 1/2 du, well, 0 to 8 will be a much bigger area, right? Would that area be twice as big since I made the base twice as big? Yes. So you see how that substitution, this part of the half that comes in, compensates for that. Because if we stretched it out, my area would have increased. Because now my height is still 3, but now my area here is base times height divided by 2 is double, it's 12. But when I do the substitution, my bounds change. Notice this half gets built into the du to say, yeah, when you stretch it out, you would get double the area. So we have to consider that and make it back half of what it was originally. And we get the same answer, an area of 6, but now our answer is a little bit easier. So I just used a simple example of a triangle to show you how when you have stretches and compressions, when things happen inside your function, they change the bounds, they change the area, but you will have compensations built in. Oh. So go to our last example. I'll only show you what I would do as my favorite way. I would say I'm going to do a substitution, and since I'm going to do a substitution, I'm going to do my bounds right away. And this one is my upper bound. No, that was my lower bound. Oh my goodness. Plugging in 0, that was my lower bound. This is my upper bound. It's changing to 1 and 4. So if my original one had, with x's, 0 to pi over 2, I guess technically you wouldn't rewrite that, would you? It's right there. Why would you write it again? So the first thing you would do would be to write this, and you would now write that my lower is 1, my upper is 4. Then from there, you go directly to that. Add 1 to the exponent and divide. Dividing by a half, we'll put that 2 out in front. So if I was doing this, I would probably have that extra step. I'd write it like that. That feels more comfortable. But you'll see that when you look at examples online, if you're looking at getting help, or if you're looking at examples in textbooks, they start to do this. They start to do, oh, I know you could do the simple calculations, so we'll do them for you just in the next step. But then when you look at one step to the next step, you're like, what the heck just happened? And then you spend a bunch of time checking the method and you're like, oh, it just didn't show their work. So I might not even show this. I might just go to this. Right? That's intuitive of what you would see and what you would think. And then I plug it in. Oops. And you get an answer of 2. Now, if you look at your notes on page 77, we continue with more advanced techniques, but all of those advanced techniques, although they're part of integration, we're not going to put them on your integration test. We're going to push those onto your next test. So we are technically done our unit for the test, even though we're not done our unit. Does that make sense? And working on the advanced techniques, when we do them, we'll still be helping you think integration and reviewing integration stuff as we're doing them. We just won't ask, and you won't be like, oh, do I have to, these harder techniques, do I have to really study them for my next test? The answer is no. So I'm going to hand out